Hi, Dr. Revis here. In this video, I will talk about intermolecular forces of butanol isomers with emphasis on physical property laboratory experiments. Specifically, I will talk about the differences between normal butanol, N-butanol, and T-butanol. Intermolecular forces are attractive forces between molecules. They are the sum of all the forces between two neighboring molecules. In this case, the question is, why are the physical properties different between N-butanol and T-butanol? We show you here 5 different physical properties of N-butanol and T-butanol. Note that they're all different. Why is that the case? In N-butanol and T-butanol, there are primarily 2 IMF forces at work. One is called London. London forces are weak IMF present in non-polar molecules. The other one is hydrogen bonding. Hydrogen bonding are stronger IMF due to polar H to O interactions as partial positive and partial negative. It's important to note that these are not permanent bonds. IMF forces are temporary interactions due to the electronic nature of the arrangement of atoms in the substance. So let's look at the difference between the London and hydrogen bonding forces in N-butanol and T-butanol. In the case of N-butanol, the London forces, which are also known as dispersion forces or hydrocarbon forces, are due to the 4-carbon chain hydrocarbon component. In the case of T-butanol, the London and dispersion forces are also due to the hydrocarbon chain. However, the arrangement of the carbon atoms in T-butanol is different than that in N-butanol. Therefore, the London forces are different in N-butanol and T-butanol. And in fact, there are higher London forces in the normal butanol than there are in the T-butanol, which we will explain in slides to come. So, in normal butanol and T-butanol, we have London dispersion forces acting in both these isomers. We also have hydrogen bonding in both isomers. The hydrogen bonding is due to the OH functionality in both molecules, with the direction of the dipole being in the direction of the oxygen. Therefore, we have a partial positive hydrogen and a partial negative oxygen in both molecules. Let's look closer at the hydrogen bonding in N-butanol and T-butanol. In this diagram, we show you the through space interaction of the partial negative oxygen with the partial positive hydrogen on 2 N-butanol molecules, and you could continue to draw this for all the molecules. We note that the same structure exists for the T-butanol as well. And because the structural features of N-butanol are different than those of T-butanol, the hydrogen bonding in N-butanol and T-butanol will be different, and that difference will be reflected in the physical properties. It is noteworthy that hydrogen bonding strengths are between 20 to 40 kilojoules per mole. This is approximately 10% of what might be expected for an ordinary chemical bond, having bond strengths between 200 to 400 kilojoules per mole. It is reasonable to assume or to conclude that solubility is very much affected by the shape of the 2 molecules. And in the case of N-butanol, it can form interactions with water molecules more easily than the crowded T-butanol molecule. Therefore, you would expect it to have a higher solubility. And indeed, in the case of T-butanol, it's only miscible in water. It is not soluble in water. However, in the case of the N-butanol, it is soluble to the degree of 73 grams per liter. This particular physical property is very much related to the interaction of hydrogen bonding of water with the OH functionality in the alcohol. And accessibility to that hydrogen bonding feature is easier or less encumbered in the case of N-butanol than it is in T-butanol. So what about the London forces? Again, London forces are weak intermolecular forces present in nonpolar compounds. Therefore, when we look at the butanol isomers, we must examine the hydrocarbon part to determine its impact on the physical properties. In the case of N-butanol, we show you a diagram of interactions of the hydrocarbon parts through London forces, which are the forces present in hydrocarbons. We note that we have more of those London interactions in the normal chain than we do in the T-butanol. In the case of T-butanol, there are fewer interactions of the hydrocarbon chains of one molecule of T-butanol with another molecule of T-butanol. Therefore, we conclude that there are fewer London forces available in the T-butanol isomer than there are in the N-butanol. This would show up at an increased boiling point. We recognize and note that hydrogen bonding does affect boiling point. However, the difference in the hydrogen bonding in N-butanol and T-butanol in itself may not be enough to account for that large difference in boiling point observed between the two compounds. Specifically, there is a 35-degree difference between the boiling point of N-butanol and T-butanol, with N-butanol being the higher boiler of the two. That difference is related to the increase in the London forces in N-butanol compared to T-butanol. That is because there are higher chain interactions in N-butanol than there are in T-butanol. One way to view this is to take a look at a geometrical model. In the case of N-butanol, it might be viewed as a rectangle. That rectangle would have more points of contact between the two adjacent butanol molecules. In the case of T-butanol, it might be viewed as a spherical model. A spherical model will have far fewer points of contact than would a rectangular model. Therefore, we conclude that there are higher London forces in N-butanol than there are in T-butanol. So, while there are two forces at play in the butanol isomers, the higher London forces are a key contributor to the higher boiling point of N-butanol. In other words, the lack of strong London forces in T-butanol results in a lower boiling point. In the case of the melting point difference between the N-butanol and the T-butanol, it is unlikely that hydrogen bonding accounts for this difference. It is also unlikely that there are sufficient London forces to account for this difference. Therefore, it is more likely that the geometrical shape of the T-butanol compared to the N-butanol is a major contributing factor. In other words, when T-butanol packs, it will pack to form more crystalline domains or ordered structure than the linear chain N-butanol. Therefore, since it has more ordered structure or crystalline domains, its melting point would be higher. In other words, spherical molecules like T-butanol will form more densely packed structures than rectangularly shaped structures for N-butanol. And higher packing density leads to higher melting point. In freshman chemistry laboratory experiments, the boiling point is determined using an apparatus as shown in this slide, where a sand bath is used to heat the sample and a thermometer is used to measure the temperature difference. A plot is made of temperature versus time, where the time is typically monitored in half-minute increments. A curve is plotted as shown here, and a trend line is taken at the plateau of the curve and extrapolated back to the temperature axis, which is the y-axis, and at that y-intercept, a measurement is made to determine the boiling point of the alcohol. In the example shown here, the boiling point of the alcohol was determined to be 82 degrees C. This boiling point corresponds to the y-intercept. You can find that y-intercept by extrapolation or by looking at the equation for the line, which is generated in Excel. The melting point may also be determined by using a plot of temperature versus time and taking half-minute increments. To carry out this experiment, the apparatus on the left of this slide is used. In this case, the thermometer is submerged in the alcohol inside of a test tube, and a wire stirrer is used to agitate the alcohol while the experiment is being conducted. After the data has been plotted, a trend line is taken on both sides of the line segments. Where the trend lines cross is the melting point of the alcohol. This can be taken by reading the graph, or you can find that value by carrying out the math, which is oftentimes the process used in many Gen Chem labs. In this case, you would take both givens, the equations for the lines, you would set those two lines equal to each other, and you would solve for x. And in this particular example, x was 4.5 minutes. Therefore, we take x and put it back into any one of the equations for the line. And in this particular case, we obtain 20.3 degrees C. So there you have it, a look at intermolecular forces of butanol isomers and how to carry out the experiment in a general chemistry laboratory.